Hi folks, this is the video recording for lab number 1, uh, assignment number 1, and it's the afternoon session that I'm referring to. So the problem that you need to do is described here. The geometry is shown here. These dimensions are in millimeters, and you're told that it's made out of steel. And this face here is clamped, and that circular face on the top, flat circular face, almost circular face, is pushed down by 1 millimeter. There's a few things you have to do. First of all, use the most appropriate element, and the only element that we have done so far are solid elements, and this is actually the most appropriate element to be used. The other thing is, it says how many planes of symmetry do you have? So use as many planes of symmetry as necessary, as exist, okay, if any. Now, in this particular problem, just think about it. There is only one plane of symmetry, and that is, for example, cutting it with the XZ plane. Now, I don't care whether you create your model in this type of coordinate system. In other words, your Z may be like that, your y like this, x like that, but it doesn't matter. I just put it here as a reference so that I can tell you what is the plane of symmetry. It is xz, okay? And then it says, make sure that there is around the hole. So here, around the circular hole, you have a finer mesh, which means do a local mesh definement. And also, what is the force that needed to cause this deformation? Okay, in other words, how much force is needed to push that entire top face, point by point by point, all the points on that top face by 1 millimeter? Okay, we're going to do that later. Now, in this particular problem, because you know that XZ is a plane of symmetry, you have two choices. Make only half of this, and then do the analysis. Or make the entire thing and then cut it and do the analysis. And that's the route that I'm going to take. I'm going to make this entire part and then split it with the XZ plane, something like that, and proceed with the rest of the problem. Okay. Now notice that when you start CATIA, by default, a product file pops up. And I suggest that you in class do not work in this. And if you do, then you're on your own. Make sure you can handle it all the way to the end. Start with the part file. We're going to do assemblies later on, analysis of assemblies later on, which means you have to, work with the product file, but not for a single part. You can do the problem as a single part in the product, but as I said, I'm not going that route. Immediately, we're going to save this thing. File, save management, save as. I made a folder for you called homework. This is the afternoon class, right? The afternoon. So it's going to be there. And say OK. And there's something else. If I look at this thing, by the way, let me look at that folder. I think it is going to be. Yeah, let me go here. Afternoon, right there. See, it's already saved it. But I want to show you something here. If you go to File Save Management, I typed something down here. This means after the name that's given there, namely Part 1, you can give it anything you want, any characters or letters that you want. So, for example, I want after Part 1 to say Nader underscore 972. So you say apply pattern. You see that? You change that. And then save it. Say OK. In that folder that I just showed you, of course, there's going to be the first part. But, I mean, basically, I re-saved it under this name. This part 1 is totally useless. You can delete it if you want. Let me see. I can delete it. This is the one that I'm dealing with. Okay, this is the part name that I'm dealing with. Okay, let's go back here. Now, so I said that, how am I going to do this? Let's see now. What I'm going to do is make the base as a rectangular rectangle with this little thing at one end of it, and proceed. So I'm going to make a rectangle of dimension, let's say uh, 80, yeah, by this way, 50, 80 by 50. Okay, so let's go there. But this is not necessarily the most efficient way or the best way. You do it any way you want, as long as you solve the problem. We don't care how you created it. Okay, so let me make a centered rectangle because I'm going to cut these things eventually. So let's see now. I said I'm going to make this thing 80. I already changed my units to millimeters. Okay, and this is 50, I believe. Okay, there we are. And the center of this circle, obviously is 80 millimeter. Just not, 80, yeah. So I'm going to make this circle of diameter. What is that? Diameter 60 or radius 30. So I go here. I'm going to make a circle here. Okay. Radius 30. Let's see now. Yeah, radius 30. Okay. And let's see now. What else do we have here? I have a circle here of radius 15. So let's go back here. This radius is 15. 15. Good. And let's do a bit of a cleanup here. I want to pad this thing up, right? So I have to get rid of some of these extra lines that are sitting there. So I go to, where is that? Quick Trim, right there. This is one of my favorite tools to use. So I'm going to get rid of some stuff here. Oops. Okay. That's fine. This one, that one, that one. Okay, good. And yeah, so exit. Where is the exit here? Right there. And then pad this thing up by 20 millimeters. 20 millimeters. Okay, right there. Now I'm going to do a little bit of a cleanup here. First of all, this thing doesn't stop there. It goes further up, and there are different ways of doing it. For example, on that face, I can sketch. Why don't I project this circle? Okay. And also project this circle. There we are. And I can actually close that. Okay, so because notice that this has to be closed. So there are different ways of closing that. For example, I can go and say, what is that circle arc? Center and arc, yeah, arc. So the center is right there. Arc goes from here to here. And notice that there is a cutout at this end. So might as well do the cutout here. 8 millimeters wide. So let me do this. Okay, but it's 8 millimeters. The width of it is 8 millimeters. 8. Good. And yeah, you can Well, maybe I should do this thing at the end. Let me do this thing at the end. Let me get rid of this. Okay. Exit. As I said, there are many different ways of doing these things. And this is going to go up by 50 millimeter, but this was already 20, so it goes up by 30. 30. Okay, good. Now, on that face, I will sketch that little cutout that I wanted to do before. I'm going to do it right now. The width of it is 8 millimeters. 8. Exit. Make a pocket all the way to the end. So all the way to last. There we are. This is the cutout. Now, what else do we have here? I have something I want to check there. Yeah. One thing, notice that this edge is not shown in the drawing right there, but it is actually there. So as a matter of fact, if you change the rendering here, you can even get rid of this rendering. If you go to different kind of rendering, let me see now. No, not this one. Oh, there you can see that that line actually kind of disappears. Okay, but I want to have it back. Okay, good. Now on this face, I will sketch. Fit it. Okay, so because I want to get this thing out, okay, so the radius of that circle is 12. The radius of that circle seems to be 12. So I go here on that face, I draw a circle. Let me see for a second, where is it? Okay, normal view, right there. Make it full circle. Radius 12. Okay, exit. Just notice something here. Let's go back to that sketch. Just notice something. I don't think this is it. Yeah, it's a coincidence. It is on that. It is on that line. Actually, no, it is not. Yeah, this point control that line. You can either say coincident, okay, or you could have put a dimension 0, for example, distance 0 between them. Exit, and then we can make a pocket of length, I believe, 40 millimeters. Dimension 40. There we are. So what you see there is this. Hopefully I didn't make a mistake. I don't think I have, but anyway, you never know. Let's go here. Save everything. Let's put material on this. So apply material, metal tab, steel on that part, and we say OK. And now, because we know that this is a plane of symmetry, I'm going to cut it right now. And as I said, this may sound crazy because we made we made the whole model knowing that we're going to cut it, but whatever is easier for you. So get on the surface space feature, you get the saw, and there we are. And it doesn't matter which side we pick, right here. So this is half of that. Okay. Yep. Save this. We're going to go to generative structure analysis, static analysis. Let me change the rendering here. Right there. There we are. Okay. Now you're told that make sure in the whole you have smaller elements. So to do a local mesh refinement, you go here. By the way, let me show you the mesh first. Right now. This is what the mesh looks like. So I'm going to deactivate this and do a local mesh refinement for that hole. Notice that it puts a default size like that. You can change it. You can make it bigger or smaller, and you can do it also on this side, both of them, on both holes. So now if you look at the mesh, right click, activate the mesh. There we are. Okay, this is too, let me do the following. Let me make this thing a little bit bigger, because you can see that already it's kind of hesitating to move. Okay, so let's activate it again. Yeah. Now, by the way, when I started, I had the choice between linear or parabolic element. Linear is faster but less accurate. Parabolic is quicker, obviously, and more accurate. But on the test, unless we give you any instructions, use linear with default element size. Okay, so and if we told you to do a local mesh refinement, please by all means do it. Good. So deactivate this. Now we know this face is clamped, so let's clamp this face. And we know that these are symmetry planes, so use a surface slider, restrained surface slider on that face and this face, the entire face is big. Surface slider, and we want to push this thing down. Okay, now in order to push it down in CATIA, first you have to actually or push it by a given amount. First you have to make that amount 0, which means use the user defined restraint. You select that in the direction Z 0, and now you can go and change it. So you go to loads under enforced displacement, you select that restraint that you just put in there. See that you just made the restraint here to push it down. Either do it from the screen or from the tree, from the tree or from the screen. And now you go push it down by -1. Now don't worry about this 25.4, whatever, these are all dimmed. Okay, this is what I did maybe a week ago to do another problem, but it's unfortunately it's going to stay there. Okay, so but I'm pushing it in direction Z by -1. Now let's go and save our analysis, file, save management, analysis, save as. If you want to keep it as analysis 1, no problem. So in that same folder, homework 1 afternoon. And if you want to add this prefix or actually postfix to the end, they add it. I'm not asking for that, but say okay. All right. So let's go ahead and run it. Nothing exciting is going to happen. This is going to stay put. This is going to go down. This is a standard message that you get because of rotation. Rotation is not the degree of freedom for solid elements, so that's just a warning. Deformation looks like that. Yeah, so you can animate it. Okay, if you want numbers, here's the numbers. You want to change the rendering, double click, average ISO, change the rendering to material shading right there. If you want to see the elements too, you go to rendering again all the way at the bottom. There's a question mark here, and because this is checked, edge and points are checked, it also shows you the elements. Now, anything that you don't like, you can either hide or don't delete these. Can't delete it. Okay, good. Oh, I didn't mean to delete it. Control Z. Control Z. There. I didn't mean to delete it. I meant to hide it. Hide. Control Z or undo is going to come to your help. Now, the last part of the problem says. Oh, well, let me show you the stress. By the way, where is the stress? I must have inadvertently closed the. Wait a minute. Where are we now? Maybe something is not. That deleting really didn't do me any good. So, you know what we should do? because I don't see the solve here. I don't see, let me see for a second, Stan. Let's see. Let me check something. Everything is there, but I don't have the plots and I don't have the compute. That being the case, what I'm going to do is, it's good that I saved. Remember? I'm going to close that. This is why it's a good idea to save always. File, it was this one, right? I think it was this. Good. There is my compute back. Everything is okay. So let me compute one more time. And because I wanted to show you the stresses also, but somehow, okay, there we are. There's the stress distribution. Big stress here. Now, these numbers, I mean, it's easy to generate good-looking garbage. So right now, we are not looking at the validity of the analysis that we have done because, you know, this is almost 300 megapascal. That is 300 megapascal, and that is beyond the yield strength of standard steel. So we are not looking at the validity of these things. We are assuming that the material does not act linearly elastic, which it won't in this case. Okay. The last part of the problem is says how much force is needed to create that deformation, the deformation needed. So here's what you're going to do. First of all, let me deactivate these plots. Deactivate this. Good. Now you go to the sensor, right click, create resultant sensor, create a reaction sensor. Now you select, remember how you push this thing down? First you made it 0 and then pushed it down. You either select this thing from the tree or select this from the screen if it does show, yeah, so there. So notice that you selected these, 0 displacement downward, and then you say update result. So it's going to be 84,000 newtons. Again, we're not talking about these numbers being meaningful. Right now, we just want to do it. Assume that we are dealing in an ideal world. Everything behaves elastically. Now, you should expect problems like this on the test. And so we're going to ask you how much force is needed to create this deformation. You have to create a reaction sensor, but then when you see this thing, first of all, don't say cancel. Maybe this is the right number, but don't say cancel because we're going to ask you to write it on your test paper. If you say cancel and you wrote this number on your test paper, I have no idea where you got it from because unless you say okay, this will not be in the tree. So I'm going to double click on this so that the guy comes back. When I mark your test, I'm going to double click on that line so this comes back. On your test paper, you should write 2 times this because this is the force needed to create the deformation for the thing that we model. And this is half of the entire part. So the actual force for the deformation needed or caused in this problem is going to be 2 times 84,199 Newton. Okay? Otherwise, there's going to be point deduction. First of all, I want to be able to see it there, where you got the number. And in this particular problem, notice that you're going to have to write double of this, 2 times that. All right, folks, so this takes care of